All right, so let's keep on digging deeper in periodic trends. We're going to be predicting trends in ionic size. We talked about elemental atomic size if it has all its electrons. Now, but if it's an ion, then how can we look at the size there? And also talk about the magnetization of atoms and ions. How can we understand if it's going to respond to a magnetic field? Okay, so can we explain patterns in the ionic radii using the information that we have here? So here I've got some ionic radii and how they compare to the atomic radii of the corresponding neutral atoms. So you notice that in each case you see a pretty big jump if we are looking at one of the cations, that they jump down pretty far in size. Now, why is this? Well, so if we look at sodium, a lot of its size is determined by that one 3s electron that's way out there on the edge. And once we remove that, there are no more n equals 3 electrons out there. We only have n equals 2 electrons. And not only that, they're being pulled tighter to the nucleus than they would be in neon with that equivalent electron configuration, because there's one more proton than there would be in neon. So that's a general trend we see. What about magnesium? So magnesium, same thing. We have the 2s electrons, and we see there's a big jump down going from beryllium, magnesium, calcium down to what we get if we take off 2 electrons. For example, here we're losing only electrons in the next shell up. All of these elements have two their valence they have 2 valence electrons of the next highest shell up in S. And so those are electrons that are quite a ways further out than the others. We get rid of them, and what remains is much smaller. As well, it's dropped down to a noble gas configuration. Plus, it has 2 more protons, so those are pulling it pretty tightly. So, which is bigger? Just guessing from this, it's going to be bigger: sodium plus or magnesium 2 plus. So, how do we approach this? Well, actually, you notice each of them has the same electron configuration. They both have the neon electron configuration. Well, so what's going to be the difference between the two? They have the same electron configuration, same number of electrons. What's different? One of them has more protons than the other. Which one? Magnesium has one more proton than sodium does, therefore has a larger positive charge, and it's pulling all of those electrons in tighter. So what we should expect is that the magnesium 2 plus ion is smaller than the sodium 1 plus ion. And let's look up here. Sodium 1 plus, the radius is 100 picometers. And down here we see, the radius is more like 85 picometers. So that checks out. If you have the same noble gas configuration, the one with more protons will be smaller. Okay, so yeah, so you can think about it in terms of the effective nuclear charge. The effective nuclear charge is an approximation to what the outer electrons feel after the shielding effects are removed. And so all of the electrons in the magnesium 2 plus are feeling a larger effective charge than sodium. They're not feeling exactly 12 protons because they're shielded by the others, but they're definitely feeling more because there's more protons there and the same number of electrons. So therefore, they must feel a greater effective charge. How about the ionic radii of anions? So what happens if we go to F minus? We see that that extra electron, it makes it bigger. We go from 2p5 to 2p6. We get an increase in the radius. You got an extra electron. And so it's all in the 2p orbital. So the orbital hasn't changed, but there's less shielding. Now all the electrons have more other friends around to protect them from the big bad positive nucleus, and so it's going to increase in size. So the anions always get bigger, even though they're not going up, they're not changing the principal shell. They have significantly more shielding, and so the outer electrons can expand because they're being shielded by that extra electron. So if we look at these isoelectric atoms, because these all have the neon on the neon electron configuration, the smallest is magnesium 2 plus, then sodium plus, and then fluorine minus, all of which have the same number of electrons, but magnesium has more protons. So this has 12, 11, 9.